Okay, our last 3.4 section of simple rational functions, part 3, and this is a long one, so I'm going to break it up into 2 videos as well. So it's never ending, but we are nearing the end. We've looked at, so aside from asymptotes that are vertical and horizontal that we've looked at, many rational functions have asymptotes that can be slanted, or what we call oblique, right? Asymptotes, slanted. So oblique asymptotes, they may be crossed, meaning that the function that we have may actually cross that asymptote, just like a horizontal asymptote. It occurs at an infinite y value for which the x values are also approaching very large positive and or very large negative numbers. So what we mean here is, if I have, see if you can see the purple. If I look at my limit, that looks okay. I think you can see that. If I have my limit as x is approaching, again, positive or negative infinity, occur at infinite y values for my function, my answer is going to be approaching positive or negative infinity. So if I'm looking at my limit to infinity and my function is getting to positive or negative infinity, then we're looking at the two extremes. And it occurs, there's a hint here, it occurs when the numerator, the degree on the numerator is exactly 1 degree higher than the degree that's on the denominator. So we have a degree 1 equation, can be found by performing long division to divide the numerator by the denominator, or you can use, we've used synthetic division. So it really just, you get the same answer, it just depends on whichever way you prefer to divide. So here we'll do an example. Nothing to do with starting the long question, just going over long division, right? So determine the equation for the oblique asymptote for the function g of x equals 2x squared plus 5x minus 6 on top over x subtract 4 on the bottom. So what we want to do is divide, right? So if I have my divisor is x subtract 4 out in front, divided into 2x squared plus 5x minus 6. And we're looking at always 2 terms at a time. So x multiplied by what is going to get me 2x squared. So x multiplied by 2x, right? So you put that above here. So again, x multiplied by 2x would give me that 2x squared, which is what I wanted, but then also 2x multiplied by negative 4 would give me negative 8x. And I am subtracting these. So again, these would cross out, but 5x minus negative 8x is like 5x plus 8x. So I'm going to get a 13x. And like I said, I bring the negative 6 down. So I'm always working with 2 terms at a time. So then back here, x multiplied by what will get me 13x? A positive 13. So then that will get me the 13x that I want. But then I need to do 13 multiplied by negative 4. So 13 multiplied by negative 4 is negative 52. And again, I'm subtracting. So those cancel out. But negative 6 plus 52 would actually give me a positive 46. And that's my remainder. So what information does this give me here? Therefore, the oblique asymptote occurs at y equals 2x plus 13. Okay. So that's my oblique asymptote, y equals 2x plus 13, just in this example, right? We're going to look at a different example. So in order to sketch here, very similar to before, the last few videos, to sketch a graph, state any restrictions. looking at my asymptotes, looking at my open holes from the last lesson, and talk about their behaviors around the asymptotes, figuring out your XY intercepts, your critical numbers, your first derivative chart to look at increase, decrease, and classifying the critical numbers. Determine the intervals of concavity and points of inflection by doing your second derivative chart. List all the information of what you have beside the graph to sketch it, and then we'll finally state the domain and range. And again, the first two here are from advanced functions, and once we start critical numbers, like let's say 3 to 5 is what we've learned in calculus in order to be able to do that sketch. So let's jump into an example. So I have g of x equals x squared minus x over x plus 1. So step 1 is always to get my restrictions on x. So again, just make sure you're telling me that. I'm just putting it over here just so that I'm trying to fill up the page so there's no dead space because I need a lot of room here, right? So my restrictions on x. My denominator, my x plus 1, cannot equal 0, so therefore x cannot equal -1, right? So what's happening there at -1? If I look at my limits, I think I can fit that in here. So my limit as x is approaching -1, write out your original expression and just plug in -1 into for x. So I have -1 squared minus -1, be careful there, -1 plus 1. So that's going to equal +1, +1. So a 2 on top, 1 plus 1 over 0, right? Or in other words, a number divided by 0, which means that that does not exist, which means that I have a vertical asymptote happening at x equals -1. So therefore, I have a vertical asymptote at a value of x equals -1. Now, if I had got, when I did this, 0 divided by 0, then I would know that the original function is not in simplified form. So because I got a value of a number divided by 0, so in the last video, if you remember, we had 0 divided by 0 and we were able to change the function into simplified form. So because I have a number divided by 0 here, then I know that, just to write out here, then I know that g of x is already in simplified form. So I don't need to worry about trying to factor that. So g of x is in simplified form already. Okay. Now let's take a look. If it's already in simplified form, from the bullets from the previous sheet, my numerator has the highest degree of 2. My denominator has the highest degree of 1. That's the numerator is 1 degree larger. The denominator is 1 degree smaller. So that means that we should be expecting an oblique asymptote, right? Because we have degree 2 on top and degree 1 on the bottom. So I just wanted to point that out here before we continue. So let's look at our behaviors around the vertical asymptote. Looking at our limits. Limit as x is approaching -1 is our vertical asymptote, but from the left of our simplified, we already know that's as simplified as it's going to be, so our original expression. Now here, if I'm plugging in, again, I'm looking for a value that's just to the left of -1. So for example, -1.001. Just take a look here. If I was to factor the top and I'd have x minus 1 over x plus 1, it's going to end up being a little bit easier when I'm plugging in those values. So again, you don't have to. I just find it's a little bit easier that way. So I said just to the left of -1, -1.001 multiplied by -1.001 minus 1 all over -1.001 plus 1. And again here, all I really care about is the sign. I don't need to have a definite value. So this would be negative, and I would have a negative multiplied by a negative. So I would have a positive on top, and then this is slightly larger than 1 and a negative on the bottom. So then my result then would be negative infinity. So again, in conclusion then, as x is approaching -1, and we were going from the left, then my y is going to be approaching negative infinity, and I can use that on my graph. So let's look at my limit approaching from the other side. So my limit as x is approaching -1, but I'm coming in from the right side. And I might as well change that then to the x minus 1, x plus 1. Again, you don't have to. So a number just to the right on the number line of -1, so like negative 0.999 multiplied by negative 0.999 minus 1 all over negative 0.999 plus 1. And let's look at our signs here. That would be negative. Negative multiplied by a negative is a positive. The 1 is larger this time, so I'm going to be slightly positive. So then I would be approaching positive infinity. So in conclusion, as x is approaching -1, but from the right-hand side, my y is going to be approaching positive infinity. Okay, and I'll use that to help me graph. I don't know how much I can fit here with my end behaviors, but I will give it a shot to start. So I'll start writing even out here so I can fit more. I think, obviously on an actual hard copy paper, you guys can probably write smaller. It's actually really hard to write on this tablet. So end behaviors to get my restrictions on y. So let's look at our limit as x approaches negative infinity. And because I'm going to get an actual value here, again, it's up to you whether you want to use factored form. If I look at my original equation, let's see what this looks like here. So again, I want to pick a larger negative number. We were always using -1,000. So I would have -1,000 squared minus -1,000. Be careful there. That seems okay to do on a calculator. -1,000 plus 1. Let you guys work ahead of me here. Pause it if you're watching it on your own. I have 1,001,000 over -999. Make sure I don't mess those two up. I'm looking at the right one. Negative infinity, yes. So I have a value that's approximately -1,002.002, which means that that's about very close to -1,000, right? So just think here, when I plug in a value of -1,000, I'm hovering in around a value of -1,000. But that was supposed to be to approach negative infinity. So therefore that means that I'm approaching negative infinity. So as x approaches negative infinity, my y is doing the same and approaching negative infinity. And again, I can use that later. So let's look at my positive limit. My limit as x is approaching positive infinity of my expression, x squared minus x over x plus 1. And again, we'll just use positive 1,000. So 1,000 squared minus 1,000. I shouldn't hopefully have to put brackets. You can, but for BEDMAS rules to do the exponent before you subtract anyways. 1,000 plus 1. So I have a value there of 999,000 after I subtract 1,000 over 1,001, obviously. So then I have a value of approximately 998.20002 I have, which means that that's very, very close. That's about positive 1,000. So same thing, we had 1000, we chose the number of 1000 to represent infinity. So if that number is representing infinity, then that means that I'm really close to positive, I'm approaching positive infinity. So same conclusion, as x is approaching positive infinity, y is going to do the same and approach positive infinity. Okay. So because we didn't get here a definite value, right? Here when we're plugging into the calculator, we've had definite values in previous videos. So because we didn't get a definite value when we were approaching infinity, right? Because what we want is a definite value. Remember how we were hovering around zero most of the videos. So my horizontal asymptote, right? Restrictions on y was 0. Here I have infinity. So then that means that there is no horizontal asymptote. So when you have an oblique asymptote, you don't have a horizontal asymptote. So we said here that our hint was we have a degree of 2 and a degree of 1. So we pretty much know for sure that we're going to have an oblique asymptote for this function. Then as expected, then we shouldn't have a horizontal asymptote, and this proves it, and vice versa. In the past, when we had a horizontal asymptote here, we had never ended up with an oblique asymptote. So you can only have one or the other. Okay, so to figure out what my oblique asymptote is, I need to do my long division or my synthetic division. So again, you can go back, or if we're in class together, we can go over how to do the synthetic division if you happen to like that more. I'm just looking at how many pages I have here. Yeah, even longer. That's why we're doing this in 2 videos and not one. Any blank page. Okay, so I'll just continue on here with my long division. So to get my oblique asymptote, I have my x plus 1, the denominator, and my numerator x squared minus x. And here you have your x squared, you have your x. If you wanted a placeholder for the constant, you could put plus 0. You don't have to. So again, we're looking at 2 terms. So x multiplied by what would give me x squared, x multiplied by x, right? So then x multiplied by x gives me that x squared, x multiplied by 1 gives me a positive 1x. And then when I subtract those, this is gone. Negative 1x subtract positive 1x. So a negative 1 subtract another 1 would give me a negative 2x, right? And again, I could bring down that positive 0 there. So x multiplied by what will get me negative 2x? X multiplied by negative 2. So then I have negative 2 times x is my negative 2x, and negative 2 times 1 is negative 2. And then keep in mind I am subtracting these. So when I have a negative 2x, that would be a plus. So negative 2x plus 2x, they're the opposite, they cancel out. 0, negative, negative, so 0 plus 2. I'm going to end up with a positive 2 there. That is my remainder. So the equation of my oblique asymptote is what's on top here, right? What my result was. So therefore, we can use OH for open hole, VA, AJ for horizontal and vertical asymptote. OA here we haven't used, so oblique asymptote. So therefore, my oblique asymptote is at y equals x minus 2. And hopefully that looks familiar to you from grade 9, right? Y equals mx plus b, but we'll discuss that closer to when we're graphing. We've got that for now. Let's move on. Let's look at my behaviors. So I don't have a horizontal asymptote, right? I have my oblique asymptote. I've looked at what's happening around the vertical asymptote. Let's look at my behaviors around the oblique. Let's look at my behaviors, around the oblique asymptote. So behaviors. I'm just putting it here again for space. I could go down here. Behavior around my oblique asymptote. So we're going to evaluate at our infinite limit. Evaluate our infinite limit. So we have our equation now. If we were to go back up above, if you recall, I guess I'll say here, when we looked at the limit, we already did this. So again, just look up in your work above. When x approached negative infinity, right, and we plugged it in, we ended up with a value of negative 1002.002, if you remember that. If I now plug in x equals, so we use negative 1000. For our large negative number, we use negative 1000. So if I use that value of negative 1000 to put into this equation, right? So y equals x minus 2, negative 1000 minus 2. Basically, I'm comparing them. So negative 1002. So I'm comparing this value, negative 1002, with this value that I got from our infinite limit. And this is the value of y on my oblique asymptote. So this is a little bit smaller, right? This value is a little bit larger. So as, I'll use a different color here. So where am I? As x is approaching, right, negative infinity, my y is going to approach this oblique asymptote, so the equation of x minus 2, and it's going to be approaching from below. That's what that means. It's going to be approaching that oblique asymptote from below, because here, this value here is, this is below negative 1002. This is below the value that I got when I plugged it into the oblique asymptote. So let's do that one more time with our positive 1000. So also to recall, so let's say I go back to green here. When I was looking at the limit, right, as x was approaching positive infinity, again, I'm just going to write of our original function, writing it all out. We got a value of 998.002. So that's why it's important to write out as many decimals as you can and not cut it off at 998. So my function itself, this is my function, right? My function is at 998.002. Let's look at what the oblique asymptote is at. So what I want to do is I want to plug in a value of x equals 1000 into my oblique asymptote equation and then compare them, right? So 1000 minus 2, I'm going to get 998, right? So my function is at 998.002, and my asymptote, right, is at 998. So how is the function comparing to the asymptote, if that's my asymptote? So as I'm approaching the asymptote, the function is slightly higher. That's a bigger number, right? The function is slightly higher than the oblique asymptote. So what we would say for our conclusion, I have in blue, is therefore, as x is approaching now positive infinity, my function, y is going to be approaching that oblique asymptote, which the equation is x minus 2, but because the function is above, we're going to be approaching again from above. So that positive just means from up above. And however you want to highlight that, because we're going to come back and use that information when we're graphing. Also, because the function was in simplified form, we already talked about there is no open hole. So I've addressed my vertical asymptote, horizontal asymptote. We don't have one. We have an oblique asymptote instead, which also means I don't have an open hole if it's already in simplified form. So I go right to my x and y intercepts now. Continue on with your steps. Okay, x-intercept, let y equal 0. What is my original function? I can make it y now, right? X squared minus x over x plus 1. Let y equal 0. 0's on the left. I know if I do that, though, I'm just going to have it equal to the top, right? So, how can I figure out what x is? I can factor out the x and be left with x minus 1, and that's starting to help me, right? Because then my one x-intercept would be 0, my other x-intercept would be 1. So therefore, I'd have an x-intercept of x is 0, y is 0, and 1 and 0. X is 1, y is 0, right? So those are my x-intercepts. So therefore, x-intercepts of 0, 0, and 1, 0. To point out there again, if you wanted to highlight that in red or something, just so we know where to find those later. So let's find my y-intercept, which means I'm going to let the x equal 0. So I have my equation here, x squared minus x over x plus 1. I'm going to leave y, but whenever I see x, 0 squared minus 0, 0 plus 1 is 0 over 1. 0 divided by 1, do that on your calculator. Don't get too far ahead of yourself. That just equals 0. It's not a does not exist or anything. It is 0. You can have 0 on top. That doesn't have any restriction. So therefore, I do have a y-intercept, right, of 0, 0. And again, if I want to just kind of highlight that so that I can come back and find that later. So I have a y-intercept of 0, 0. So next would be to get my critical numbers. So to get the first derivative here. And again, as long as I have a function, it's still useful to do my, my charts. So let's use next, critical numbers. So I already have my original function written out here, right? I don't really need to write it out. If you want to write it out again, you can. But to get my first derivative, I'm going to move it over. I can see here in my answer that it's pretty long in the numerator. So let's do f prime of x here. So again, quotient rule. I'm going to do the derivative of the top, which is 2x to the power of 1 minus 1. So 2x minus 1 times whatever the denominator is. Quotient rule is subtract. The derivative of the bottom, be careful, is just a 1 times whatever the top is, x squared minus x. And then divide by, not too bad, x plus 1 squared, the denominator squared. Then it's a matter of cleaning it up. In terms of cleaning it up here, I don't have any like values I can multiply here, like constants. So we can FOIL this to clean up and then gather like terms. So I would have here 2x squared, right, plus 2x minus 1x minus x minus 1, and I can continue on. That 1 just isn't going to change anything, but bring the negative in. So a negative x squared and then plus x, right, all over x plus 1 squared. And where's that going to leave me here for my numerator? So I have 2x squared minus x squared. So that would just leave me with 1x squared. And if I wanted to kind of say that those are taken care of. And then 2x minus 1x is just 1x plus x will get me back to 2x, positive 2x. And then I only have one constant, so that minus 1 all over x plus 1 squared. So again, I need to solve for x, right? So what I want to look into doing is factoring. I'm just gonna, because again, I don't have room, I'm just gonna come over here. So in terms of factoring, that's a simple trinomial. Can I think of two numbers that multiply to -1 and add to 2? Well, the only numbers that multiply to 1 are 1 and 1. If I'm multiplying to a negative, one has to be positive and one has to be negative. Can that in any way add to 2? Unfortunately not, because then that means it's more work for us. So when I can't simple trinomial factor, what's left, guys? I have to use the quadratic formula now, right? A little bit more work. Hopefully we're faster at it than we were when we originally learned it in grade 10. So again, technically I should show that I'm setting my first derivative equal to 0. So 0 equals x squared plus 2x before I solve for x equals x plus 1 squared. And the reason why I was looking at the numerator is because, again, when I cross multiply, like again, I'm not really going to show anymore. 0 times the denominator is just 0. You're going to end up with just the numerator. That's why that's all I was focusing on. So I'll have to move this, but we have for our quadratic formula, our a value is going to be 1, our b value is going to be 2, and our c value is going to be -1. So we have one negative there. So we'll go ahead and clear this. You guys can write the formula ahead of me, get working, plug it in, see if your answer matches mine here. So we are looking at x's. So x equals -b plus or minus b squared minus 4ac all over 2a. And again, we had our a was 1, our b is 2, our c is -1, just to have it all in front of me there. So we have -b, -2, plus or minus b squared, 2 squared minus 4 times a times -1 all over 2a, but 2 times 1, I just go ahead and just do that multiplication right away for the denominator and make it 2. I'm just noticing like I'm kind of wasting space here. I'm just going to move over. -2 plus or minus, let's get that down to 4. 2 squared is 4. -4 times 1 is -4. -4 times -1 is +4. So 4 plus 4, I get down to 8. And now it's where I can break it up. So I have x equaling -2 plus the square root of 8 over 2, and I'll get that value, and x equaling still -2, but now minus the square root of 8 all over 2, and I've already done this, right? You guys work on it ahead of me. So find out what the square root of 8 is. -2 plus the square root of 8. Maybe if your calculator can do it in that order, -2 plus the square root of 8, then divide by 2. I have approximately 0.4. Then for -2 minus the square root of 8 divided by 2, I have approximately -2.4. So those are my critical numbers, right, for my chart. So therefore, my critical numbers, so something's happening around there. Critical numbers are at x equals numerical order, right? So do the negative first and then the positive, numerical order from left to right. So when I'm looking at my number line, I call it a number line. It's your x-axis, but still basically a number line going from negative to positive, positive infinity, negative infinity. What are the values that I have? So be careful here. Again, I want to put them in numerical order. So I have the -2.4 and I have the 0.4. But did I have any other x value? So go back. Right? Didn't I also have a vertical asymptote at -1? So this is where you want to include all those restrictions, anything that you found, right? So I have -2.4 would be the farthest to the left. Then I would have -1. Then I would have 0.4. And I should say what those are. So 0.4 is a critical number, CN. -2.4 is a critical number, but my -1 is a vertical asymptote, because I have to be careful when it's talking about increasing and decreasing, right? That it's not increasing and decreasing. There's a separation there with the vertical asymptote. So now I actually have 4 intervals. So my chart's going to be relatively big here with 5 sections, and I think I can fit that in here. Factors of the first derivative, f prime of r, are we g here? I wrote down, yeah, g prime of x. So just to keep it consistent to the question, factors of g prime of x, and then I'm going from -infinity to -2.4 interval, from -2.4 to -1, from -1 to 0.4, and then from 0.4 to positive infinity. Just fits. And then I have to go find my factors of the first derivative. Before I set it equal to 0, what was my numerator and denominator there? Let's see. Yeah, I have it here. I'll just put it up. So I had 0 equaling x squared plus 2x minus 1 over x plus 1 squared. So my numerator is x squared plus 2x minus 1. Make sure you've got the positive and negative signs in there. And then I have the x plus 1 squared. And then I need my overall sign of the first derivative. And then I'm just going to erase this. I know what my critical numbers are up there just for now. Then I have my increase or decrease right over the original function. Shouldn't I be putting g here? Yes, I should. No problem. My overall sign of, I shouldn't erase part of it because my brain just finishes it off. My overall sign of g prime of x, and then increase and decrease of g of x of the original function. And again, just put some lines there to keep it easier for me to see where your answers are lining up with. And let's do this. So smaller than -2.4, -3 kind of makes sense there to me. So just be careful if you want to write this out. -3 squared is 9, and then -6, and then -1. So I'm still going to be positive. -3 plus 1 would be -2, but -2 squared would be positive. So a positive, again, this is quotient. Dividing by a positive is positive. So here I'm increasing over this function, this interval of the function. Between -2.4 and -1, yeah, let's pick -2. -2 squared is 4 plus 2 multiplied by -2 is -4 minus 1. So I have a negative there. And then -2 plus 1, -1, but squaring it is going to be positive. So a negative divided by a positive is a negative. I would be decreasing over that interval. Between -1 and positive 0.4, there's a 0 in there. 0 squared 0 plus 2 times 0. So that's going to be a -1. So that's going to be a negative. 0 plus 1, 1 squared is positive. So again, that's going to be negative when you divide them, and that interval is decreasing as well. And then we have between anything bigger than 0.4. So 1, you could pick 2. 1 squared is 1 plus 2 times 1 minus 1. So that would still be a 2. That would be positive. A 1 plus 1, 2 squared would be positive. So positive divided by a positive, and I am increasing over this interval. I normally like to write down below. I didn't consider that here. I'm running out of room here. So, okay, I'm just gonna say it. I'll see how I can write it. Make my line a little thinner. So again, what is happening here at the -2.4? If I look up above, that's a critical number. So if that's a critical number and I'm increasing and then I'm decreasing, then I have a local max. So again, I'm trying to fit this in, guys, sorry. I have a local max at x equals -2.4. Should be, actually I can probably fit that in. Oh, I'm not going to fix that. A max at x equals negative 2.4. Here, I'll just do that. So then what's happening at -1? At -1, be careful, that's my vertical asymptote. So if that's a vertical asymptote, right, there's a break in there. I'm decreasing, I'm continuing to decrease, but that's a vertical asymptote, which you can't go through, right? So just make note here that here, right, there's a vertical asymptote at x equals -1. So just saying I don't have a local max or min there. And at 0.4 was another critical number. So something is happening there. So if I'm, just to put off to the side here, if I'm decreasing and then I'm increasing, then this is going to be my local min at x equals 0.4. So I do have a maximum, a local max point, I do have a local min point, but one of those values there is just a vertical asymptote and not a max or min. So to figure out the coordinates of my local max and local min, unfortunately, I'm going to stop the video after this. It'd be nice if I had just a little bit of room to finish, but I don't. So I'm going to just clear this for my conclusion. And there is more steps to do, but again, just to kind of chunk up the videos so they're not taking up, and maybe if they're longer, I'm thinking they might not load as well for you at home either. To find the local max, make it a little bit thicker, see it better. To find the local max at x equals -2.4, right? Because we found we have a local max at x equals -2.4. Remember, sub the x value of 2.4 into your original function. So it was x squared, sorry, that should be negative 2.4 squared, right? Minus x minus -2.4. So be careful with all those negatives. Negative squared minus another negative all over x plus 1. So -2.4 plus 1. So I have here 5.76 plus 2.4 all over -1.4, right? So that gives me a value of approximately -5.8 I have. Hopefully you match me there. So therefore I have a local maximum at an x value of -2.4 and a y value of -5.8. So I would need to know that local max for my graph. So again, if I wanted to make that all red, or if I had a highlighter and just indicate that that's information I will need for my graph. And then to find out my local min, I had the local minimum at x equals 0.4. So if I plug 0.4 in for x into my original expression, I have 0.4 squared, right? Minus x squared minus x minus 0.4 over x plus 1, 0.4 plus 1. And there I have 0.16 minus 0.4 all over 1.4. And here I had a value of, an answer of approximately, I have -0.17, negative 0.17. So therefore my local minimum point is at an x value of 0.4 and a y value of negative. Again, if we're graphing it, we can make that -0.2, right? And just to point out there that that's my local minimum, and I'll need that for graphing. So I can just highlight that in some way. Local min and local max. So I've done my first derivative chart. We are on critical numbers. So we are on number 5 next, right? Determining the intervals of concavity and points of inflection. So to get the possible points of inflection, I'm going to want to get the second derivative if you wanted to get started there ahead of me.